As a hobbit taking multivariable calculus might say, we've had one way to multiply vectors, yes, but what about a second way to multiply vectors? That's our goal for today. Now, the way we're probably thinking of is we take a vector, dot a vector, and out comes a number. Well, a number isn't a vector, it's a different type of object. What we'd love to do is get a vector, multiply by a vector, and be a vector. So, there is something that can happen. It's called the cross product. And so let's take some time and take a look. A quick recap. We already have the scalar product, which says a number times a vector. That's really for changing the length, possibly reversing it if you multiply by a negative. The dot product, which is great because the dot product has this beautiful geometric interpretation. It's the magnitude of the two vectors times the cosine of the angle between them. So it's good for angles, including right angles, which means orthogonal. And we can also do projection. So today, the cross product, which by the way explains why we call the dot product, because we have to have a way to distinguish the different types of products. So we have a dot, which shows up as the dot product. The other product, to cross, we use a little cross, which is that looks like a little tiny X. So it takes a vector, cross a vector, and out comes a vector. Now, before we begin, we need to be really clear that there's a lot of limitations that come with the cross product. First off, it's going to be very strange, and if you don't believe me yet, keep watching. But there's something else. The dot product works in any dimension. The cross product works in dimension 3. Now you might say, ooh, what's special about dimension 3? And I'm going to tell you the great secret right now. It turns out that 3 has this beautiful property where if you take 2 plus 1, you get 3. And this equation here, that is the reason why the cross product only works in dimension 3. Now you might think of, that doesn't really seem like much of an equation. But we'll get into it in just a moment and explain why does the 2 and the 1 equal 3 say that it only works in dimension 3. So here's what we're going to do. We're going to start the cross product by first saying what are some things we want to specify, and then from those consequences will emerge about what's the definition. So let's start with some properties we want it to satisfy. Now when we talk about a vector, we can always think about it as having two aspects, a direction and a magnitude. Let's start with the direction. So here's our key principle, and this is probably the most important thing about cross product. If you only remember one thing about cross product, remember the following. When I take the cross product of the vectors u and v, I want the result to be perpendicular to u and to v. Now, remember I wrote down that equation 2 plus 1 equals 3. Where are those numbers coming from? The 2 are coming from u and v. So you put two vectors in. The 1 is coming from what comes out. And so you have two inputs and one output. And so that gives you a total of 3 directions you're dealing with. Well, it turns out that if we're dealing with three-dimensional space, if you have 2 directions, then essentially what you have is a plane. And you say, okay, what's a natural third direction? So we can imagine that we have here a vector, we'll call it u, and another vector we'll put over here, we'll call it v. And so vector u and vector v lie in this plane. The natural direction, a unique direction, is the direction perpendicular to the plane. So that's why we have this uniqueness. If we went up to higher dimensions, u and v would still be in a two-dimensional object, but now there's lots of dimensions going around, you don't have uniqueness. Well, actually, hold on, we're not quite unique yet. Take a look at the picture. What's the challenge? You see, sure, there's this thing which is perpendicular, but we could be going up or we could be going down. So we've really narrowed it down to 2 possibilities. We have to break the tie, or a better way to say it is we have to break symmetry. So you might have heard of something called the right-hand rule. it's based off of your right hand. So this is my right hand. So I'm going to demonstrate. Now, one of the nice things about right hands, it's actually true for left hands as well, is they have these flexible things. We tend to call them fingers. Now, what do? Well, what you do is you imagine that this part where your fingers join the palm, that's where you would put your two vectors coming together. Your finger parts are going to be u, the palm part is going to be v. So if you came here, you'd have u pointing along the fingers in v, and now wherever your thumb points, that's going to be the direction of u cross v. Now, one of the nice things is, you'll notice, unless something has gone terribly, terribly wrong, your fingers only can close in one way. It's not like you can somehow bend them backwards. So that's how we know we can break symmetry. So there's only one way where you can put u and v together, so you can close your hand. And that's why we know that it will uniquely determine our direction. Okay, so that's direction. Don't worry too much about the right hand rule. We will rarely appeal to it. And when we do, we say, look, there's other ways to think about the situation. And here's how we understand orientation. But at the end of the day, right hand rule is really about orientation, which really means breaking symmetry. Okay, so that's the direction. It's perpendicular to what we start with. Again, the most important thing to remember about cross product. It's perpendicular to the two vectors we began with. Now the magnitude. We're going to say that the magnitude of the cross product is the magnitude of u, magnitude of v, sine of theta. So that's another way we can say, well, look, that has a nice geometrical meaning, because I can talk about here's the length of this vector, here's the length of that vector, and I can talk about the angle in between, so I can do the sine of the angle. The last property is we're going to have that it distributes nicely. So the distribution is nice because it means we can do expansion, things like foiling. So in other words, u plus v cross w, I can multiply the w in. U cross w and v cross w. Or w cross u plus v, I can distribute the w in. W cross u plus w cross v. Now, if we have just these three properties, everything else about the cross product can be derived from these three facts. Okay, so if we know direction, we know magnitude, and we know the fact that it distributes, life is good. Okay, so let's go and do some really simple properties. First off, there's some things which are really strange. If I take the cross product of u and v, and I compare it to the cross product of v and u, I flip. In other words, there's a negative. So it means the order in which you multiply things matters. Well, where does the flip come from? If you go back to the picture here, you see when I have u and v, I'd have to have it here, so my thumb would have to go that way. But when I swap the roles, I'd have to turn upside down. So I'm reversing the direction of the output. So that's why u and v versus u cross v versus v cross u, they're going to have opposite directions because of that breaking of symmetry from the right hand rule. Now, what about this u cross u equals 0? Why would that have to be true? Well, come here to the magnitude. If I look at u cross u, that says I'm looking at u twice. The angle between u and itself is 0. They're the same vector. So the sine of a 0 degree angle is 0. So that says the magnitude of u cross u is 0. Well, there's only one vector that has length 0, and it's the 0 vector. So that's how we know that the magnitude of a vector with itself is 0. All right, well, that's interesting. Indeed, if I take a magnitude of two vectors which are parallel, I'll always get 0. So in some sense, you could say, hey, there's a way to test if two vectors are parallel. Just check their cross product and see if it's 0. It's a terrible way to test it. There's much easier ways to test if two things are parallel. You check to see if they're scalar multiples. But of course, we have options. Now, let's start with our basic I, j, and k. So, remember, what are I, j, and k? Well, they are corresponding to the direction of the axis. So you have I, j, and k. So you can just start working your way through. And you can say, well, notice that all of these vectors are perpendicular to each other. So So they're mutually perpendicular. They all form right angles. And since they all form right angles, we have that the sine of the angle between it is 90 degrees. I, j, and k are themselves each unit vectors. And so the output of a cross product with I, j, and k with another I, j, k is going to have length 1. Because if you go back to the formula for the magnitude of a vector with length 1 times the magnitude of a vector with length 1 times a sine of 90 degrees is 1. So really we just have to figure out what direction do things point. Now you just sort of work your way around. So I, j, k, well, okay, here's the x-axis. Here's the y-axis. So x-axis, y-axis, thumb points in the z-axis. So you can just put it right on top. So I cross j equals k. And then you can say, okay, what about j cross k? Well, you got to move around, but j cross k, this is not very compelling when I wave my hand on the screen. You should try it yourself. J cross k is I, and you just keep going. K cross I, so here's your fingers, there's your palm, boom, and then you're pointing in that direction. And so forth and so on. If you flip, j cross I is minus k cross j is negative I, and I cross k is negative j. So now we know how to take these vectors I, j, and k and cross them with each other, and we're ready for a formula. Because remember, all our vectors in 3 dimensions are nice combinations of I, j, and k. So here goes our formula. We're going to take our vector ABC and we're going to cross it with our vector DEF. Now, ABC is really AI plus GB times J plus CK. Here we have DI plus EJ plus F times K. Well, you start to expand. Remember, we said that the cross product is going to respect the distributive property. And when we talk about foiling, which is about distribution, it says you take one term from the first, one term from the second, in all possible ways. And then we say, okay, put it all together. So, for example, AD, I cross I, AE, I cross J, AF, I cross K, and so forth and so on. So since there's 3 possibilities here and 3 possibilities there, we get 9 terms. But now we know how to handle these things. For instance, there's a couple of them which we can knock out right away. Anytime we take a vector across itself, we get 0. So the I cross I, the J cross J, and the K cross K all go away. Now the remaining ones, we can say, well, we know what happens to those. So for instance, we go back to what we just talked about. If I want to know what is I cross J, well, we look at the picture, I cross J is equal to K. So that we can replace this by K. I cross K is negative J, and so forth and so on. So you just go through and work them out one by one. There's 6 things that have to be figured out, and they're pretty quick to derive. So now we started by taking the cross product. We did our foiling, use what we know about I, J, and K, and we get down to some nice combination, and then we just group. We say, okay, where are things with an I? Well, there's a BF and a CEE with a minus. So BF minus CE goes in the first component. J, there's a minus AF and a positive CD. So CD minus AF goes in the second component. And then finally with the K, there's an AE and a minus BD. And so there's the formula. And you're probably thinking, we have to memorize that? I don't have it memorized. So instead, we're going to talk about an easier way to remember it by saying, here's a process to find it. So we want to figure out a nice process that results by saying, start with 2 vectors, and the output will be what you see here. Now to get to that, we've got to do a little bit of a side detour. So the side detour is about determinants. So let's do a little bit of perhaps reminding, perhaps saying things. First off, what is a determinant? Well, what we do is we have something called a matrix, and if you're not familiar with that, just think of it as there's an array of numbers. And we're going to take that array and say, I want to get down to a single value. And we're going to call that value the determinant. So for right now, just think of it as it's a special value associated with an array of numbers. Now, for a 2 by 2 array, so for example, A, B, D, E, that's 2 by 2. And when I say 2 by 2, 2 rows and 2 columns, then the determinant, which I'll put with a sort of a set of lines here, it's not quite absolute value, but you can think of it somewhat. There's a size involved. We'll get into that in a little bit. Is found by taking A times E minus B times D. And at this point, you're probably thinking, whoa, I've seen something that looks like A times E minus B times D before. Indeed, if you look back here, A times E minus B times D. Ah, okay, so maybe there's a connection. Well, now that's for 2 by 2. 3 by 3. 3 rows, 3 columns. So let's suppose that the first row has entries, we'll call them X, Y, Z, then A, B, C, and D, E, F. Then the determinant is this quantity. Well, it's sort of like, what? Where are these coming from? How do you remember these? It says, well, there's B times F times X, or C times D times Y, so forth and so on. So here's how you find that. There's really 2 approaches. The one I like to think of is thinking about diagonals. So I'm going to think about the diagonals of, well, when I say diagonals, I'm going to start with the columns. So I have the columns here, and I'm going to rewrite the first 2 columns. Now you don't have to rewrite, but let me show you what I mean by the diagonals. We're going to go and say, let's look at all our diagonals as we go down. So you'll see as we go down, there's an X times B times F. There's a Y times C times D. And there's a Z times A times E. So that's what we're going to get if we go downhill. Now, we could have gone in a different direction. We could have gone up. So here we could have gone this way. So when we go down, we add. When we go up, we subtract. That's the rule. So here, if we go in alphabetical order, this would be B times D times Z. And the next one would be C times E times X. And the last one would be A times F times Y. And if you look, that's what we have here. BFX, CDY, ZAE, and then, well, it's a little bit rearranged, but that's what we get. There you go. So that's one method. Now there's a second method you may be familiar with, which is called cofactor expansion. And here's how it works. What you do is you pick any row or any column, but almost all the time you go with the first row. So here's the first row. And we say we're just going to work along the first row one at a time. And we're going to say, all right, let's suppose we do an example. So let's use the first entry. So what we do is we say you grab the first entry. So there's the first entry. Then you imagine that you cross out the first column and the first row. And you see there's a little smaller matrix left here. And, oh, there's a typo here. That's not correct. Let me fix this. This should be B, C, E, F. Sorry about that. That's a typo. So, that's so embarrassing. Okay, well, we'll fix it, right? We'll fix it. So B, C, E, F. And so now what happens from there? Well, what happens from there is you say, look, I have my entries. And now there's a little 2 by 2. And so you do BF subtract EC, because you go do the 2 by 2 rule. And notice what you have. You have an X times BF, good. And an X times EC, great, perfect, just what you need. And you just keep doing the same thing. So that's the first entry. Then you go to the second entry, similar process. You say, okay, grab the second entry. Imagine crossing out the first row, and the second column. And what do you have left? We have a little 2 by 2, A, C, D, F. So AF minus CD. Well, AFY, and then you have plus CDY. Good, it works out. Here's the thing you have to be careful of. And when people do cofactor expansion, when they make a mistake, this is what they forget. I haven't said it out loud yet, so we haven't had a chance to forget it, is when you move along, you say you add the first piece, subtract the second piece, add the third. So don't forget this minus. That's actually important. A lot of people forget that. And now you come to the end, and same process, right? You take this entry, cross out the first row, cross out the third column, and you have A, B, D, E, and you do your little 2x2 determinant, and life is good. So, why are we doing this? It turns out, and this is the really cool thing, that if I want to take the cross product of two vectors, I can do the following. I'm going to take the determinant of a very special matrix. The first row are vectors, I, J, K. The second row are the entries of the first vector, A, B, C. And the last row, D, E, F. And now, the thing is, take your determinant and expand it like you would here, and lo and behold, it's exactly what the cross product should be. You can actually check, because we can compare. So for instance here, really what would happen is you'd get, for example, BFI, CDJ, AEK, CEI, AFJ, BDK, right? That's what would happen if we replace XYZ by IJK. And now if you go back and you check, well, let's check what's with the i's. BF times I, and what do we have here? There we go. See? There's a BF times I. What else has an I? CE. All right? Right there. CE. And it's being subtracted. And you go through and you check, and lo and behold, the 6 terms that show up in this determinant are exactly the 6 terms that are left when we worked it out. And so it's beautiful. And so we have this really, it's a very nice, elegant way. So whenever I'm doing a cross product, I'm always going to think of, don't memorize the formula, memorize the way to get there. So think about taking a determinant of a 3x3 matrix. One of the things that's kind of strange, if you've taken determinants of 3x3 matrices before, is you always think of it, well, okay, I get that it's numbers. Are you allowed to put vectors there? Is that okay? And the answer is yes, you're okay. You're allowed to put all sorts of objects in. And you just have to make sure that in some sense you can justify doing operations with those objects. In our case, when we do the determinant, we're multiplying these vectors I, J, K by numbers, which is scaling, and that's okay. So, good. So now we have a way to compute. We can actually do cross products now, and it just takes time. One word of warning, computing cross products is not a super fast task. And so you have to be careful, and it's easy to make mistakes. So what you want to do is figure out how can you check your work. So you sort of have two options. One, redo everything, and two, be smart. Now, the danger with one is it might take a lot of time to redo everything. So we don't want to do that. We want to be smart. So we want to use option 2. So what's the be smart? So here we go. So to check our cross product, what can we do? Well, we think about what's true about a cross product. And the answer is there's this nice geometrical fact that the cross product has to be perpendicular to what we started with. So what we do is we say, okay, at the end of the process, we have an answer for what we think U cross V is, and we just do a quick dot product, because dot products are very quick to check. So if I take whatever I think the cross product is, and I dot it with U, what needs to happen? They have to be perpendicular, and therefore, I have to, must be 0. So if you take a cross product and you dot it with U, and it's not 0, 100% guaranteed a mistake was made. Which means, go back and check your work. Now, if you're paranoid, the other thing to do is check it with V. And again, that should be 0. And if in both cases when you take the dot products you're getting 0, you almost certainly did it right. It's not guaranteed, but for most of the time when we do it in terms of applications, it's good enough. And we're good to go. So this is sort of a nice rule of thumb to do and a nice habit to get into. Look for ways to check your work which are a lot faster than just redoing it. And cross product has a natural way to do that. So don't forget. Check, check. So in some sense, this is appealing to the fact that we know something about the direction. And almost always when we talk about cross product, we're going to say, hey, we need to find something which is perpendicular to 2 particular vectors. And we're like, hey, cross product, that's fantastic at finding things perpendicular to 2 vectors. But you know what? Cross product also has a magnitude. And so let's see if we can think of a way to use the magnitude. So here we go. So what are we going to do? Well, our goal is to say, does the magnitude of our cross product have a nice geometrical interpretation? So here's what we can say. Suppose I think of my 2 vectors. I have a magnitude of u and a magnitude of v. And now I want to understand what's true about the following. Magnitude of u, magnitude of v, sine theta. Well, we can actually think of the picture. Suppose I have my angle theta, and I'm going to do a similar thing that we did when we talked about dot product. Just imagine, excuse me, just imagine dropping straight down. So this forms a right angle. Now, previously when we had cosine theta, the cosine theta looked at the adjacent part. Sine theta is going to look over here. So if I have that this is the length of this side, is the magnitude of v, then this side over here is the magnitude of v times sine theta. This is one of our nice properties about triangles and right triangles. So I can relate the sine to the opposite and the hypotenuse. Now, look at the picture. What do we have here? Well, we have a parallelogram. Now, how do you find the area of a parallelogram? It's base times height. Well, we've got our pieces. The base, I can now think of it as having length, magnitude of u. The height, all right, well, that's this length, magnitude of v sine theta. So magnitude of u times magnitude of v sine theta, according to our property, that's the magnitude of u cross v. So now we say, ha-ha, cool. So we can say that our magnitude of our cross product can be used to help us find something about an area of the shape where we have the u and v as the sides of a parallelogram. Now, of course, keep in mind, this works in dimension 2. Now, maybe you don't like parallelograms. Maybe you like triangles. You say, well, can I still do something with triangles? And the answer is yes, because there's this fancy thing that is the following. A triangle is half a parallelogram. So you can see that if I have a triangle, lo and behold, you can say, look, if I just take this side here, you can take this side, move it parallel to there, take this bottom side, move it parallel to there, and now my triangle is exactly half. These two pieces are the same shape, just moved. So if I'm looking for the area of a triangle, I say, well, that's not so bad. That's half the area of a parallelogram. And so it's half of the magnitude of u cross the magnitude of v. So now we can find area of triangles. Well, again, we can find area of triangles as long as we're in dimension 3, right? Because that's where we have cross product. So the way this can work is if I'm in dimension 3, and then I say, okay, look for the vectors that make up the sides of the triangle, and take their cross product, find the magnitude, divide by 2, and life is good. But you might want to say, can we go further? Can we do more? Is there anything else we can do? Good. Great question. And here's what the last thing we'll talk about. The volume of a parallelepiped. Now, what's a parallelepiped? Well, it's like a three-dimensional parallelogram. if you think about parallelogram, you have sort of these parallel sides. Parallelepiped says you have parallel surfaces. So in other words, it's like you take a box, but then you've tilted it in some various combination of ways. So that's what is a parallelepiped. Now, how do you find the volume of such a thing? Well, it actually is kind of nice. If I'm trying to find the volume of a parallelepiped, it comes down to saying, I'm going to take the area of the base times the height. Now, let's think about what the picture should be. I'm going to have my base be this part right here, the part that you see shaded. And in this diagram, we have that U is on one side, V, which is the same vector as down here as it is up here, is on another side. And now I say, well, look, if I want the area of the base, it's an area of a parallelogram. So I know how to find that area. That's the magnitude of U cross V. Perfect, perfect. What's left? Well, the height. So we have to tackle the height. So first off, we have to understand, what do we mean by height? Well, what the height would be is if you came along this last side, which we call vector W, and wherever you stopped, you were to drop straight down so that it formed a right angle. This length here is the height. So that's what we're after. Now, the question is, how do we find it? Well, here's where we come into play and think about our geometry. What do we know? Well, what we know is that U cross V has to be perpendicular to U and V. So, in terms of the picture, if I think about my vector U cross V, what will happen is that it's going to be coming, if I put it here, it's going to be coming up in such a way by some fairly large amount so that it's perpendicular to U and it's perpendicular to V. So it's perpendicular to U and V. In particular, and this is the really important idea here, this direction of U cross V is parallel to this segment that we use to make the height. And that's going to be the really important idea. So this direction of U cross V is the same direction as what we're using to make our height. Well, how do we use it? So let's focus on this angle between U cross V and W, because that's an angle that we can sort of visualize, and also it's an angle between vectors. So I have U cross V, I have W, I have an angle theta. This angle in this corner will match this angle over here. So this angle matches that angle. And that's because of the fact that this U cross V is parallel to this height, and then you have this line segment W which goes in between. So you have these opposite corners match. So if you think about it this way, you have, here's your height, here's your U cross V, they're parallel, here's W which connects them, and what we're saying is that the angle here has to match the angle there. That's some geometry. So now we say, okay, that's great, and our picture is starting to get crowded, but we're almost done. Look at what you have. You have this beautiful triangle. So we'll mark it here in red. This triangle right here. It's a right triangle, which is good. So it's not the wrong triangle, it's a right triangle. And if we draw it here to the side, we have our angle theta in the corner. The hypotenuse is formed by W. So the length of the hypotenuse is the magnitude of W. And now this part right here is the height. So we have our height. And we look and say, well, hey, we have this great thing going on. The height is the adjacent side. The length of W is hypotenuse. That's cosine. So I can say then the height is the length of W times cosine theta. Now you might notice something I've done here. I've thrown some absolute values in. Where are they coming from? They're coming from the fact that cosine theta could be a negative value. And so that's why we always think of height as a measurement. Measurements should be positive. So that's what the absolute values are doing, just to making sure we have a positive value. So what do we have? Well, we're going to take our base, which we already found, our height, and if we multiply them together, we're going to get, lo and behold, the absolute value of the magnitude of u cross v, our base, magnitude of w cosine theta, our height. Here's the really cool thing. Look at what you have. You have the magnitude of two vectors times the cosine of the angle between the two vectors. That's a dot product. And so this is the same as the vector w dot u cross v. And then you take that number, whatever it is, it's a number, and just make sure it's positive. And that's the volume. So that's actually fairly easy to compute. Now, it doesn't matter which one is w, which one is u, which one is v. You can put them in any order. The end result will be the same. You might get a sign change, but remember, since you're taking the absolute value, at the end, it's all going to work out. Now, here's sort of the fun fact. If you remember back to how we did cofactor expansion, we had the I, j, and k. Well, when you take the dot product times a vector, well, what's happening is you can think of taking this original vector and you're replacing I by whatever the ith piece is. You replace j by whatever the jth piece is and k by whatever the kth piece is. So that's the equivalent to saying, hey, this quantity of w dot, this u cross v, is the same as taking a 3 by 3 determinant. First row is w, second row is u, and the third row is v. And then at the end, just make sure you take the absolute value. So what does that tell you? In some sense, it says the following: determinants are a volume of some sort. So that's the information that's being stored inside of the determinant. Now, this fact is a little bit less useful. We will definitely use the fact that when we take a cross product and take the magnitude, that forms the area of parallelograms. That's going to be an important idea as we go on, particularly towards the latter part when we do multivariable integration, which is a fun topic. We are really going to be using a lot the fact that when we take the cross product, we form perpendicular vectors. And that's going to be an application that's going to find pretty quick use. But in general, the cross product is a really interesting, beautiful, three-dimensional. Don't forget, you've got to be in 3 dimensions to use it properly. And so, well, we should go and probably do some practice with it. The more practice you do, the easier it'll get. So get to work. See you soon.